Hey everyone, and welcome back. So today, we're going to cackle one of the most important metrics in all of computer vision, mean average precision, or as pretty much everyone calls it, mAP. If you've ever wondered how developers figure out which AI model is truly the best at seeing the world, well, mAP is the answer. So let's get right into it. How can you tell if one AI model is actually smarter than another one? Let's say we have two different AI models looking at the exact same image, trying to find things. How do we get beyond just a gut feeling and arrive at a real objective score? Let's just jump into a real-world example to see what I mean. Okay, so take a look at this. Your gut feeling might give you a clue here. The model in green, that's efficient to TED. It seems, I don't know, a little over-eager, right? It's drawing a ton of boxes, maybe too many. But then, on the other hand, YOLO V3, in yellow, looks like it might have missed a few cells right near the edge. So, can we really trust our eyes here? Judging performance just based on what looks right can be super tricky and honestly, pretty misleading. Right. So to get past that gut feeling, we need a way to actually quantify this stuff. We need one single, reliable number that can tell us objectively which model is better. And not just on one image, but across thousands of them at all different levels of confidence. And that number, well, that's mAP.
Okay, so before we can really get mAP app, we've got to start with its two most basic building blocks, precision and recall. Seriously, think of these as the absolute foundation for everything else we're going to talk about.
All right, first up, precision. The easiest way to think about this is it's all about how accurate the model is when it actually makes a prediction. So when the model points to something and says, hey, that's a red blood cell, precision is just asking, okay, but how often are you actually right? It's all about the quality of the predictions it decides to make. And on the other side of the coin, we have recall. This is all about completeness. If there are, say, 10 white blood cells in this picture, recall asks, out of those 10 that you should have found, how many did you actually find? It doesn't care so much if the predictions were perfect, but whether the model managed to find everything it was supposed to. And this is where it gets really interesting, because there's this natural tension between these two ideas. They're almost always in a trade-off. Think about it. If you want super high precision, you can just tell your model, look, only make a prediction if you are absolutely 100% certain. And yeah, it'll be right a lot, but what's the downside? It's going to mess a ton of stuff, so your recall will be terrible. On the flip side, if you want high recall, you can tell it to flag everything that might even possibly be relevant, but it's going to make a lot more mistakes, and that'll drag its precision way down. This shark analogy is perfect. It just makes it all click. Imagine I asked you to name every type of shark. You'd start with the easy ones, right? Great white, hammerhead, tiger shark. That's your high precision. You're nailing it. But as you try to get every single one, to get full recall, you might start guessing. A cow shark? Your confidence just tanks, and your precision goes down, even while you're trying to push your recall up. Okay, so we've got this trade-off, this balancing act between being right and being complete. The next logical question is, how do you even capture that relationship in a single, useful picture? Well, the answer is a tool that shows us exactly how a model's performance changes as we start tweaking its confidence level. And that tool is the precision recall curve. It's basically a graph that gives you the entire performance of a model at a glance. It puts precision on one axis, recall on the other, and it shows you exactly how one changes as you demand more from the other. And how you make one is actually pretty straightforward. So first, you start by telling the model to be super strict, like only make a prediction if it's 99% sure. At that point, your precision is sky high, but your recall, it's probably pretty low. Then you just gradually lower that bar. You let it make predictions it's less and less sure about. And with every single step down, you plot the new precision and recall values. And voila, that's what creates the curve. Now, this is great, but comparing a bunch of wiggly lines is still kind of a pain. So we can simplify it even more. Instead of trying to compare the entire curves, we can just calculate the area underneath it. That single number has a name, average precision, or AP for short. A bigger area just means a better model, one that manages to keep its precision high even as it's finding more and more stuff. Okay, so we've nailed down average precision, AP for one type of object. We are so close to the final score now. We just need to add a couple more layers to get from AP to the big one, mAP. But hold on a second. There's another little problem we have to solve first. With object detection, it's not enough for the model to just say, that's a platelet. It also has to draw a box around it, in the right place. So how do we decide if that box is good enough to count as a correct prediction? Well, we do that with a really clever metric called intersection over union, or IoU. It's actually a pretty simple idea. All it does is measure the percentage of overlap between the box the model drew and the actual real box. A score of 1 is a perfect match, and a score of 0 means they didn't overlap at all. And now, finally, we can put all the pieces together. It's really just 3 steps. First, we calculate the average precision, that area under the curve, for each and every object class. So we get an AP score for red blood cells, another one for white blood cells, and one for platelets. Then, to be extra thorough, we do that entire calculation again and again, each time with a stricter rule for what counts as a correct box. We might calculate all the APs using a 50% IOU overlap, then do it all over again at 55%, then 60%, all the way up to a really tough 95% overlap. Finally, you take the average, the mean, of all of those AP scores across all the classes and all those different IOU levels. And that final number? That is our mean average precision. All right, so with all of that under our belts, let's go all the way back to our original mystery. Let's pull up the final scorecard for our 2 models and see what the numbers actually tell us. So here they are. The table breaks down the average precision scores for each type of cell. You can see right away, both models were really good at finding white blood cells. I mean, look at those AP scores, over 95%. But when you look at that final mAP score, the one that averages everything together, well, the winner is crystal clear. It's efficient dead with a final mAP of 84.31%. It wasn't even that close. And this, right here, is the big aha moment. The model that, to our eyes, looked a little messier, the one that we thought was making too many predictions. It was actually the better, more reliable model when you measure it properly. This is the perfect example of why we need a metric like mAP. It totally protects us from our own human biases and just gives us the cold, hard truth. So, there we have it. We have our winner, our single number. But it's always worth asking a final question, right? mAP is an incredibly powerful tool for comparing models. But what details might that one single number be hiding from us? I mean, looking at the scores for each class gave us a bit more insight, but what else gets lost when we boil down such a complex system to just one number? Definitely something to think about. Thanks so much for joining me.